A very good morning, class 12th. The agenda is another topic of coordination compounds, a unit of class 12th. I finished the valence bond theory in the last class, where the video of the tail end complex was to be completed by you yourself. Now moving on to the crystal field theory. This is one of the very important topics of the chapter coordination compounds in class 12 CBSE syllabus. Now before I actually move forward to this, what we need to know is what is a coordination compound. A coordination compound is a compound between ligand and a transition element. Now what is a ligand? Ligand has lone pair. So this is your lone pair of the ligand and it is a lone pair donor since it donates the lone pair via coordinate bonds. So your bond is to be formed, this acts as the donor. Now what is a transition element? They have partially filled D subshell, which means their D subshell has some electrons. Now, when this bond is formed, the ligand donates or contributes to a coordinate bond like this, which means your transition metal should have empty D orbitals or other orbitals where the lone pair can be donated and you end up in the coordinate bond formation. Now, what is crystal field theory then doing here? Crystal field theory takes into account the effect of lone pair of the ligand on the d orbitals of transition metal. How does this lone pair affect the d orbital of transition metal? Actually, what we are trying to say is that the lone pair repels electrons of the transition metal. Hence, it affects the D subshell. Since we have to study the D subshell, you need to know what are d orbitals and how do they look like. Now, in this particular topic of crystal field theory, we would be taking up only two types of complexes. One is octahedral and the second is tetrahedral complexes. What is the major difference? In an octahedral complexes, you would have 6 ligands. In case of a tetrahedral complex, you would have only 4 ligands which will be approaching the transition metal. Now, these 6 ligands will be approaching the octahedral complex and here the 4 ligands would be approaching the octahedral complex. Now, there are 6 ligands, therefore, it would have more repulsion because more the electrons, more would be the repulsion. Here comparatively, you would have a lesser repulsion or lesser CFT. The effect of crystal field theory is less in case of tetrahedral complexes. Of course, there are other complexes, but they are not in your syllabus. So, we would only be stressing on octahedral complexes and the tetrahedral complexes. Now, before we move on further, we need to understand the shapes of the d orbitals. These you had done in class 11th, structure of atom chapter. Now, d orbitals are total of 5 types. The first is dxy. A dxy orbital is a interaxial orbital, that is the electron cloud is in between the axes. Is that okay? Coming to dyz, this is again an interaxial double dumbbell which is also in between the axis. Fine. I have deliberately not taken the third axis because you do not require the third axis, so that their diagrams in 2D are much more clearer. Coming to dxz, this is the x-axis, this is the z-axis. Again, this is also an interaxial double dumbbell. So, these 3 are interaxial, which means they are between axes. Is that clear? These 3 would also be called as the T2G orbitals in case of crystal field theory. This you should understand. Coming to the next two types of d orbitals. The next is a dx square minus y square. This orbital is an axial double dumbbell, which means the orbital is on the axis. It is not in between the axis, it is on the axis. Similarly, you have a dz square. Dz square is one of the d orbitals whose shape is altogether different. This is also an axial suborbital, but it is not a double dumbbell. It is on the z axis and there is a disk on the xy plane. So these are the shapes of the d orbitals that you should know. These two are the axial d orbitals, that is, they reside on axis. Fine. Also, these are known as the Eg orbitals in the crystal field theory. This should be understood to you. From now onwards, your shapes of the 5 d orbitals are like this, out of which now you need to know they are classified separately. T2g are 3 orbitals and Eg are 2 orbitals which are on the axis are called Eg, and which are in between the axis, as you can see, they are called as the T2g orbitals. Fine. Now let's study how is an octahedral complex different from a tetrahedral complex. Now your transition metal is here. This is my transition metal, which is having 6 ligands around it, which are oriented like this, and all angles, as you can see, are 90 degrees. Do you understand if I say that these 2 ligands are on one axis, these 2 ligands are on the other axis, and these 2 ligands are on the third axis? That means these 6 ligands are on axis, which means these 6 ligands will approach the metal from the axis. Since they are on axis, therefore they will affect the Eg orbitals, and the reason is that your Eg orbitals, as you can see, are also on the axis. So when the ligand approaches the octahedral geometry, 2 ligands approach on the x-axis, 2 approach on the y-axis, 2 approach on the z-axis, and these orbitals get affected. There is repulsion in these orbitals. So this affects your Eg orbitals, or the axial orbitals face more repulsion because your ligands are approaching from the axis. Now what happens in case of a tetrahedral complex? This is your central metal, the transition metal, and your ligands are approaching tetrahedrally like this, and you very well know the angle is 109.5, which also means none of them is on the axis. In this case, you have 4 ligands which are not on the axis, because axis pe hote to angle would have been 90. The angle is 109.5, so they are not on the axis, therefore they affect the interaxial d orbitals. As we had already done, what are the interaxial d orbitals? These 3, dxy, dyz and dzx. So when your ligands are approaching tetrahedrally, they are not approaching on the axis, they are approaching somewhere in between the axis, because the angle is 109.8. Since they are approaching somewhere in between the axis, they will affect these d orbitals. The electrons of these d orbitals will be more repelled when the ligands approach tetrahedrally, while electrons of these orbitals of d subshell will be more repelled when the ligands approach octahedrally. So these 3 are affected in tetrahedral complexes, while these 2 are affected in octahedral complexes. The reason is they are on the axis. Fine. So in case of octahedral, your 6 ligands are approaching on the axis, so they affect your EG. While in case of tetrahedral, 4 ligands are not approaching on axis, so they will affect the interaxial d orbitals, that is the T2G are repelled. Fine. Now moving on to the concept of crystal field theory. I will be first talking about the crystal field theory for octahedral complexes. And when I say octahedral complexes, it's understood there are 6 ligands and they are approaching on the axis. Fine. Now, supposing I have, this is the d orbital. Let us take this is dxy, this is the yz, this is the xz, this is x square minus y square, and the last one is dz square. Now, these all are written together, that is they have same energy and they are called as degenerate. Now, when the ligand approaches, this is the state which happens when your ligand starts acting. When the ligand approaches, the d orbitals get increase in energy. Their energy gets higher. Energy of the d orbitals due to the effect of ligand, and this is due to repulsion. And why is there repulsion? The d orbitals of the transition metals will have some electrons. These electrons, I am not drawing them. These electrons, let us say these electrons, you have 5 electrons, 1, 2, 3, 4 and 5. Now these 5 electrons, when the ligand is approaching, will be affected because ligand is approaching via the lone pair. The lone pairs of the ligand will repel these 5 electrons, and this repulsion will cause the energy to increase in these 5d orbitals, all of them. Now as the ligand approaches further, now the ligand is moving much more closer. How many ligands are approaching? 6 ligands. Where are they approaching? On the axis. If they are approaching on the axis, these 3 are the T2G orbitals. These 2 are the EG orbitals. Now in this case, do you understand, if the ligands are 6 and they are approaching on the axis, which out of these 2 will be more repelled? These, which means their energy will increase, which means you should understand that if the ligand further approaches, you have 6 ligands which are approaching, it will lead to increase in energy of the EG, and comparatively there would be a lesser energy for T2G because T2G is in between the axis, while ligand in case of octahedral complexes approach on the axis. Now this gap between these two EG and T2G is your crystal field splitting energy, and it is represented as delta and a naught. This is not naught, this is O. This O is for octahedral complexes. Just for your information, you should understand that your delta naught, that is delta octahedral, is dependent upon number 1, your charge on transition metal and strength of ligand. If there is more positive charge on the transition metal, ligand will approach more with their lone pairs. If there is stronger ligand, it will go closer to the d orbitals. If it goes closer to the d orbitals, it will affect more and the splitting energy will change. This delta naught is not constant, it changes when the ligand changes. Fine. Also, there is another concept which says that on the basis of, I feel that it is due to the energy conservation, what we say is there is a decrease in energy here and an increase in energy here. This increase in energy is given as 3/5 for each of the 2 orbitals. So 3/5 plus 3/5, that makes it 6/5, while here there is a decrease in energy which is by 2/5 per orbital. So 2/5, 2/5, 2/5. This also is 6/5. So a decrease of 6/5 and an increase also of 6/5. Moving on to the CFT for tetrahedral complexes. Now you should know that when I am talking about tetrahedral complexes, there would be only 4 ligands, number 1, and they would be approaching at an angle of 109.6. So they are not approaching on the axis, they are approaching interaxially. If they are approaching interaxially, then out of the orbitals that you have, let us take, this is the d orbital, this is dxy, this is dyz, this is the xz, this is x square minus y square, and this is dz square. Now when the 4 ligands are approaching tetrahedrally, now which orbitals will be affected? It will affect these 3 orbitals more because they are in between the axis. These will be less affected because they are on the axis. So when the ligand starts to approach, the first thing that happens is energy is increases. So here the energy increases for all the d orbitals when you have the 4 ligands approaching. Now as the 4 ligands approach further, if they come much more closer, you should understand that these 4 ligands with their lone pairs, supposing I have again 5 electrons in these d orbitals, the 4 ligands will approach all these and they will affect all these, so all their energy would increase. That's one. Now when this starts forming bonding, when it starts approaching it closer, then these 4 ligands are approaching the central metal atom via the 109.5 angle. That means they are approaching in between the axis. So these 3 orbitals are found to increase in energy because they are repelled more because the ligand is approaching on the T2G, while the EG orbitals would comparatively have a lesser energy. Now in this also, this gap between the two is called as your crystal field splitting energy, represented as delta T. Delta T means the splitting energy for a tetrahedral complex. Again, both the things are applicable to delta T also. That means delta T also depends on the charge of the transition metal and the strength of the ligand. That means this value will vary again. Also, you have here, you should understand that delta T and delta O can be compared. If I compare both of them, then it is observed that generally your delta T is less than delta naught. Why is that? The reason is that in case of delta T, you have only 4 ligands approaching, while in case of octahedral complexes, you have 6 ligands approaches. As you can see, I have made it a smaller difference in energy. Here the energy difference is larger. Also, if the notice, this is important, if transition metal and ligand are same, if they are both same, then it is observed that your delta T is equal to 4/9 of delta naught. So if the transition metal and the only if they are same, then for the same metal and same ligands, if there are 4 ligands approaching, it is tetrahedral complex. If there are 6 ligands approaching, it is octahedral complex. Then octahedral के comparison में your delta T is always going to be less, and it is by this factor found, but it is only applicable if these two conditions remain same. I'll take an example to give you a drill of the concept. I hope you are understanding the concept really well. This is by Seema Makhijani, trying to make chemistry easier for you. Now let us take, supposing I have a complex which has got D4, that means 4 electrons in the D subshell, 1, 2, 3 and 4. Now when the 6 ligands approach, we very well know that the 6 ligands are octahedral, that is you have 90-degree angle, therefore you have axial approach, so your Eg energy rises as compared to T2G. Now if I say so that delta naught is higher, if delta naught is higher, then what would be the electronic configuration is the question that I am asking. That is the first. If delta naught is high means you have to fill these 4 electrons in these. Let us start filling them. 1, 2, 3. This much is easier because this is lower in energy. They will be filled first according to Aufbau. Now what about the next electron? Now will the next electron move up? That depends what is the energy difference. As I said, the energy difference is large. Since the energy difference is large, the 4th electron cannot move up. You will have to draw the 4th electron here. So your electronic configuration in such a case would be T2G has 4 electrons and EG has 0 electrons. Therefore, here again the number of unpaired electrons would be 2, and this becomes your paramagnetic. Fine. The second case could be, let us say you are given that delta naught is less than pairing. Delta naught is less. Your interest is to only understand whether it is less or more. If delta naught is less, that means when I start filling these, in this case what would happen, I'll just illustrate. This is again a D4 complex. Let us take a 3D complex with D4, and you have again 6 ligands approaching, and this 6 ligands are your weak ligands. If they are weak ligands, this gap is less. That means your delta naught is low crystal field splitting energy. Now you have to put 4 electrons. 1, 2, 3. Now the 4th electron can easily jump up because the energy difference is less. So your 4th electron moves here. So if you are asked to write the electronic configuration for such a case where you have D4 configuration and delta naught is less, your configuration way of writing would be T2G has 3 electrons and EG has 1 electron. Now in this case you have 4 unpaired electrons, therefore this becomes more paramagnetic. Is that clear? Let us do a question to understand it better. The question says you have to illustrate the crystal field theory and give the electronic configuration in terms of T2G and EG for these two complexes. Now have a look at these two complexes. What is the central atom? Your central atom is iron. What is the oxidation number of iron? It comes out to be, please check, X for this one, -6 is equal to -3, therefore it is +3. And you can see it is same in both of them. The only difference is in this case you have Fe as 3 positive, therefore the configuration would be argon 3d5. You can check that later. Your configuration for Fe3 positive is 3d5. So this is your complex with 5 electrons of iron. I am talking about the 3D for Fe. Now when the ligands approach, now there are two options. If your ligand is this, in both the cases it is an octahedral complex. Therefore the splitting has to be Eg would be here and T2 would be here. Now what we need to know is this gap is called as delta naught, and you should understand that halides and water are weak ligands. Therefore delta naught would be low. So if I am talking about this complex, if this is the complex, your delta naught is less. For this complex it is less, so your electrons 5 are to be filled 1, 2, 3. Now the gap is less, so the electron can jump up 4 and 5. So in first complex for your Fe, F6, 3 minus, the EC would be written as T2G3, EG2. I hope that's clear. But if the complex is the other one, as you very well know, in case of Fe, CN6 with 3 minus, both of them are D5 configurations. In case of D5, now in this case your Cn is a strong ligand. Since it is a strong ligand, so your delta naught is going to be high. Therefore, when you fill up the electrons are to be filled, this gap is large. So when I fill up the electron, let me illustrate it for you. The electron filling would happen like this. You have 2 electrons to be filled here and you have 3 electrons to be filled here in the T2G and EG, and mind you this gap is large. Why is this large? Because the ligand is strong. Now I need to fill up how many electrons? D5. If I want to fill up D5 electrons for this complex, 1, 2, 3. Now will the electron jump up? No, because the gap is large. So the electron will have to pair up here. So your configuration becomes T2G5 and Eg is 0. In case of this complex, that is how you would write the configuration. Just to summarize it up, your crystal field splitting energy for a tetrahedral complex is always low. Why is that? Because you have only 4 ligands. Whereas when I talk about delta naught, that is for an octahedral complexes, it is always high. The reason is here you would have 6 ligands. Now if this delta naught is high, generally speaking, delta naught is greater than delta T. Therefore, do you understand, if the gap is large, therefore probability of pairing of electrons is more in which case? If the gap is large, in case of octahedral, the electron will not jump up. Since the electron will not jump up, it will start pairing. The probability of pairing of electron is more in octahedral complexes. Since the electrons are getting paired, we say they would form low spin complexes. Whereas in case of delta T, whereas tetrahedral complex is low, therefore no pairing because the electron will jump up, therefore more unpaired electrons. Therefore, high spin complexes are found in case of tetrahedral, while in case of octahedral you generally have low spin complexes. Low spin means nothing but less unpaired electrons. If you are not clear with this, please watch my video on valence bond theory, which was just prior to this. I hope I have tried my best to give you the grasp of the topic for crystal field theory. Please do well in life. Stay safe, stay healthy, keep in touch, keep writing your remarks and keep promoting my videos. Bless you kids. Do well in life. Bye.